Hello everyone, we continue proving more and more trigonometric identities. Let's have a look at the graph of cosine function. Cosine function has a graph that is completely symmetrical with respect to the y-axis. And this is because the cosine function is an even function, and we know that all even functions are symmetrical with respect to the y-axis. So if you have an angle like theta, let's say 20 degrees, on the right hand side, then the angle negative 20 degrees or negative theta is also on the other side of the y-axis, but again on the graph of the function. So this means that if I grab 2 points, let's say A and B, these 2 points have x coordinates that are a negative of one another or opposite of one another. For example, 20 degrees and negative 20 degrees, 30 degrees and negative 30 degrees. But both of them have exactly the same y coordinate. So both of them have the same cosine value, in other words. So this means that cosine of negative theta on the left-hand side is equal to the cosine of positive theta on the other side. You can quickly check this with the calculator. Punch in cosine of negative 45 degrees, you will see 0.707, and then punch in cosine of positive 45 degrees. Again, you will see 0.707. So the conclusion is that cosine of negative theta is equal to cosine of theta. And there you go, that is just another identity for you. It doesn't matter if you select 20 degrees or 30 degrees or 35 degrees, whatever angle, it doesn't matter. Always cosine of negative angle equals cosine of positive angle. But is this the case true? Like, is this the case for sine function? Let's have a look at the graph of sine function. You know that sine function is an odd function. It's not an even function. And it doesn't have symmetry about the y-axis, but instead it has symmetry about the origin. So if you grab a point, let's say point A, with like an x-coordinate of theta or like 30 degrees, then the symmetrical point on the other side, and symmetry is with respect to the origin here, would be another point like point B, which would have the negative theta x coordinate, which would be the opposite of the x coordinate of point A. But in terms of the y coordinate, because point A is above the x-axis, it would have like a positive y value, and point B is below the x-axis, it will have a negative y value. But those distances, due to symmetry, are perfectly equal to one another. So basically, the y coordinate of point A is negative the y coordinate of point B. And when I say y coordinate, it means the sine value of the function, obviously. Sine value of the angle, obviously. So this means that sine of negative theta, which represents actually this negative, negative y value, is equal to negative sine of theta itself. So sine of theta is a positive value, let's say like 0.7, but this one is negative 0.7, okay? So that's why we say sine of negative theta is negative sine of theta, so that negative 0.7 will be positive 0.7 basically. And similarly, if you divide sine by cosine, that would be tangent. So if you divide the right sides, you get negative tangent of theta, and that means that the tan of negative theta is equal to tan of positive theta. That is another identity right there. If you apply the reciprocal identities, similarly, cosecant of negative angle will be negative cosecant of the angle. Secant of negative angle will be just secant of the angle itself, because secant is reciprocal of cosine, obviously. And cotangent of negative theta would be negative cotangent of theta. So these are negative angle trigonometric identities. So in this other diagram, we have a unit circle whose equation is x squared plus y squared equals 1. And you see the corner is like 1, 0. And we have a point P with some coordinates of a, b on the circumference of this unit circle. And it makes an acute angle of theta. Now, this is the basically green angle in standard position. Now, I wonder what is the sine of angle theta here. So using the formulas we all know, it is y over r basically, right? And here, we know r would be a squared plus b squared, of course, under the square root sign. So sine theta is y over r. In this case, would be b over r. And what is r? It's square root of a squared plus b squared. You can have like numbers here. It doesn't matter. Maybe like a is like 3. No, it can't be 3. A is like 0.8 and b is like something else. Such that a squared plus b squared equals 1 squared. Because here, in fact, r is equal to 1 because we selected a unit circle. But if it was not a unit circle, then the radius of the circle would be square root of a squared plus b squared. So perhaps it was a good idea to pick a unit circle because we have a radius of 1, and it makes life easier because b over now, r would be b over 1 now, okay? And similarly, cosine of the angle in the first quadrant would be x over r, which is actually a over 1, okay? Tangent would be y over x, so that would be b over a, okay? All right, so these are sine, cos, tan for the angle in standard position in the first quadrant. It's an acute angle. Now consider the red angle, which is an angle in standard position whose terminal arm is located in the second quadrant. And the measure of the angle happens to be pi minus theta. So we have another angle, theta, on the left-hand side. We called it reference angle or related acute angle. And that happens to be exactly equal to theta. So if you're selecting like 30 degrees on the right, we have 30 degrees on the left. So pi minus 30, or 180 degrees minus 30 degrees, would be 150 degrees. So basically, the red angle has a measure of 150 degrees, for instance. But generally speaking, it is pi minus theta, okay, because we're considering these two acute angles the same. And I wonder, what is sine of this pi minus theta angle in standard position? So definitions are telling us y over r. But y over r, the y value is b. And I can write here b, and r is just 1. So I got b over 1 before when I was finding sine of theta, and now sine of pi minus theta again is giving me the same value. Because point P and Q, they have the same y coordinate of b. So my conclusion here is that sine of pi minus theta is equal to sine of theta itself, because both of them are b over 1, that is b. In terms of cosine of pi minus theta, because cosine is x over r, so here x is negative a. So if you divide negative a by r, you get negative a over 1. But remember, cosine of theta was positive a over 1. So that means that cos of pi minus theta is actually negative cosine of theta. And that's a second conclusion I come up with. And I'm going to write negative cos theta equals cosine of pi minus theta. And needless to say, if you just divide these two, you can derive the identity for tangent, but still using the diagram, we can say tan of theta is b over a, but here, tan of pi minus theta, which is actually y over x, it is going to be the y coordinate, which is b, over the x coordinate, which is negative a. So it will be negative b over a. So you see that tan theta is b over a, but tan of pi minus theta is negative b over a. So that means that tangent of pi minus theta equals negative tangent of theta, which of course we could have derived this by just dividing left sides and right sides of the former two identities. But even these formulas will give you the same result. And if you flip both sides of these three equations, or use the reciprocal identities, you can say that cosecant of pi minus theta is equal to cosecant of theta. Secant of pi minus theta is negative secant of theta. And cotangent of pi minus theta is negative cotangent of theta. So these are three other trig identities that we can derive. So that was the story of the red angle in standard position, whose terminal arm was located in the second quadrant. The measure of the angle was pi minus theta. Now, what if we have pi plus theta, and what if the terminal arm is lying in the third quadrant? You see this black dashed line I have drawn, this angle in standard position. It gives us, again, mind you, I selected angle theta below the x-axis exactly equal to angle theta above the x-axis. So if the top angle is like 30 degrees, the reference angle, known as related acute angle, then the bottom is also the same amount in terms of degrees. So we have pi plus theta, and that gives me a point R on the circumference of the circle, and the coordinates of point R are negative A and negative B. Now, why negative A? Because it has exactly the same x coordinate as point Q, and why negative B? Because it is B units below the x-axis, therefore it's negative B. Point Q was above the x-axis, where the y coordinates are always positive. So having said that, the question is, what is sine of pi plus theta? So y over r gives you negative b over 1, which is negative b. But we said that sine of theta, we said before, it was equal to b. So that means that sine of pi plus theta is actually negative sine of theta. So this gives me a new series of identities. Sine of pi plus theta becomes a negative sine of theta. And you can try this with the calculator. Grab like 10 degrees, for example. Punch in sine of 180 plus 10, which is 190 degrees. Punch in sine of 190 degrees. You will see a decimal number on the screen of the calculator. You can try it right now. And that would be exactly equal to negative sine of 10 degrees if you try. You see that one is negative the other. The whole decimal number is there, except that the sign is negative this time. Negative sine of 10 degrees is equal to sine of 190 degrees, which is 180 plus 10 degrees. Okay, so the next one is cosine of pi plus theta. So cosine of pi plus theta would be x over r. X is negative a, and r is 1. And cos theta, before we said it's 1. So that would be also negative cosine of theta. And tangent, again, we can divide these two equations. It will be positive tangent of theta, or we can say y over x would be negative b over negative a, which is b over a, and tan of theta, before we said that it was actually b over a. Therefore, they are equal. Using the reciprocal identities, we can say cosecant of pi plus theta, which is 1 over sine of pi plus theta, would be negative cosecant of theta, and here negative secant of theta, but this one would be positive tangent of, cotangent of theta, and this was cotangent, so positive cotangent of theta. So this way, you see that we are deriving so many identities, okay? And there's even more. We can have sine of 2 pi, which is like 1 full revolution, and then minus theta. So I can just expand this idea, and I can say, okay, we have an angle here, theta. So 2 pi minus theta. So it will be an angle in standard position whose terminal arm lies in the 4th quadrant this time. So 2 pi minus theta, the answer would be negative sine theta. Cosine of 2 pi minus theta would be positive cosine of theta, and tangent of 2 pi minus theta would be negative tan of theta. Reciprocal identities you can automatically derive, so I don't write it here, but it would be cosecant of 2 pi minus theta, which is equal to negative cosecant of theta, and so on and so forth. And if you try 2 pi plus theta, for example, sine of 2 pi plus theta, so that would be 1 full revolution plus another theta. So we're talking about coterminal angles here, which we have talked about them in the past. In that case, I think nothing is going to change, because you know that coterminal angles are sharing the same terminal arm. So the same green color terminal arm we have for angle theta, it will be the same for the angle in standard position whose measure is 2 pi plus theta. So we are going to get sine of theta itself, cosine of theta itself, and tangent of theta itself. It's not difficult to try with a calculator. Punch in sine of 380 degrees, which is 360 plus 20, right? So sine of 380 degrees equals sine of 20 degrees. If you check, you see that it's matching. Or even cosine of 380 degrees is the same as cosine of 20 degrees. You get the same decimal number on your calculator, on the screen of your calculator. So these are not difficult to verify. So this way, we end up with a whole bunch of, series of identities, which in future, of course, we can use. These are all, sets of identities that we have derived. And as I said, in future, we can use these identities. And I try to prove them using the angles in standard position and using unit circle and partially using the graphs. We will prove more trig identities in future. These are still, basic ones. Thank you.